Okay, welcome back after a long break, and we will be starting with a new topic, but it's not a brand new topic. It has some relation with what we were discussing, and if you remember, what we were discussing was Bayesian linear regression. So we are continuing with Bayesian linear regression, but we are now trying to relax the assumptions that we had. And what was the assumption that we was working with? That our prior is a conjugate prior. And because our prior was a conjugate prior, we could do many things, including closed form solutions and all those stuff. Now, as soon as we relax that assumption, many things will not be possible. And we'll see and try to understand how we can deal with such a scenario. Okay, so that is the kind of the broad idea that we are starting today. And this will continue for, I don't know, maybe 6 to 7 lectures. So sampling method will continue for 6 to 7 lectures. And we will be talking about different sampling methods. I don't think today we will be talking about any sampling method that is directly applicable to Bayesian linear regression, but we will start with the most basic one. And from there, starting Saturday, because Saturday is a working day, we will actually look into sampling methods that you can actually use for, let's say, problems like Bayesian linear regression. Okay. So just to quickly recap, we have till now discussed Bayesian linear regression under two circumstances. The first one was not so realistic, and in that case, the noise variance or the noise precision beta was known to us. And if the beta is known to us with a conjugate prior, you can do the derivations, and all the key formulas that you will need are shown on the slide. Okay. And then we also discussed about a more realistic scenario where the noise variance will not be known a priori to us, and that is something we will have to infer from the data. So that is a scenario where mu and sigma square are unknown and are to be inferred, right? This will be the scenario where mu and sigma square are unknown and needs to be inferred. So you have to put a prior on them, and in that case also you can do all the derivations. The prior, conjugate prior, becomes Gauss inverse gamma, and we did all of that stuff as well. And this is kind of where we stopped last time. And this is majority of your homework 1, practical 1, and all of those things are this only, right? So now, continuing from that point, in Bayesian linear regression, as I said, we were working with the assumption that our prior we will be using is a conjugate prior. Okay. So till now, we have discussed Bayesian linear regression with conjugate prior, right? And because of conjugate prior, we were able to get closed form solutions, closed form of the posterior, closed form of the predictive distribution, right? So this allowed us to compute posterior and predictive distributions in closed form. It was possible because we were using conjugate prior. But if you remember, I said it earlier that conjugate prior is a strong prior, right? We have already discussed that conjugate prior is a strong prior because it kind of limits your posterior to a certain class of distribution, and basically the same class as the prior. Okay. So conjugate prior is a strong prior. Conjugate prior is a strong prior. And what is the issue with conjugate prior being strong prior? Well, it is possible that your actual prior belief cannot be formulated as a conjugate prior. And in that case, as conjugate prior is a strong prior, so the prior will be significantly different or can be potentially significantly different from what your actual belief about an event is. So it is okay to have a prior which is weak prior, not exactly matching your belief, because in that case that prior is a weak prior, so it will mostly be governed by the data. But in this case, what will happen is that you are not modeling your exact prior, which is not a good thing to start with. But along with that, you are using a strong prior. So whatever results you will get will be influenced by the prior, which anyways is not the prior belief that you had. Clear? What is the issue? And therefore, this is not something that is desirable. So basically, conjugate prior is a strong prior, and it is often the case that our prior belief it is often the case that our prior belief cannot be expressed as a conjugate prior. In which case, if we are forced to use conjugate prior, we are being forced to use a wrong strong prior, and wrong strong prior is not a good thing. Okay. On the other hand, if we want to use some other prior which is not a conjugate prior, we cannot do Bayesian inference analytically. Okay. On the other hand, it will not be possible to do Bayesian inference analytically if our prior is not a conjugate prior. Other hand, it is not possible to solve the inference problem analytically without a conjugate prior. Now, can you remind me what will be the issue if we try to do Bayesian inference? What will be the bottleneck? What will stop us from doing things analytically? You remember the Bayes law? Probability of the posterior is equal to prior times likelihood divided by the model evidence. And model evidence is what? Probability of D, which is a high dimensional integral. So it is the model evidence that stops us from doing things analytically. So just to write things mathematically, you are trying to find out this one, which is equal to probability of theta, which is my likelihood, probability of, which is my prior, probability of D given theta, which is my likelihood, divided by probability of D, which is my model evidence. And model evidence, if you have to calculate, or if I write the total or the Bayes law in the most popular form, then this is equal to integration of probability of theta dash or theta, probability of D given theta, D theta. Okay. This is the known form of the Bayes law. And it is the denominator that creates the problem. And why does it create the problem? What is theta? Theta represents what? Model parameter. Now, in a linear regression problem, suppose I have 1000 input variables, 1000 input features, and I am just using linear. Even in that case, I will have 1000 plus 1, 1001 theta. And if I am using something like a neural network, then I will have theta in the order of, at least in the order of lakhs, and it can go up to trillion. Like GPD type of models, they have in trillions. Okay. The lower order GPD like Llama and all those things, they have in billions. So that means this will become a billion dimensional integration. And doing a billion dimensional integration is not trivial, obviously. And in almost all the cases, not possible also analytically. It will not be possible that you will do a high dimensional integral by, or you will integrate out theta, which is in the high dimensional space. So that is the problem. Okay. So be very clear that the problem is in the high dimensionality associated with theta. If theta was not high dimensional, then we were good. Then there was no problem. Okay. Mostly, I mean, even in that case, you cannot guarantee that integration will always be possible analytically, but mostly we would have been good, but that never happens. Like even for a very small problem, we will realize theta will be 10 dimensional. Now, how many times have you solved a 10 dimensional integration in your life till now? Maybe never. You can understand the challenge, even for a small problem with 10 theta. Okay. So the bottom line is that model evidence, which is the denominator, is intractable if you are not using a conjugate prior. And in that case, you cannot do things analytically. Okay. And if you cannot compute the posterior analytically, forget about predictive distribution, because predictive distribution uses the posterior. So nothing can be done analytically. Okay. So this is intractable. This is generally intractable. Okay. This portion is generally intractable. So now the question comes, what is the solution? Two things can come to your mind. One is always use conjugate prior. Probably not a good idea, and the reasons we have already discussed. The second thing that can come to your mind is that, can we somehow approximate now? Or can we somehow bypass analytical solution and go towards some other routes which will not be analytical now, but which will be reasonable, okay, under certain conditions, mathematical conditions. And one such possibility is to use sampling based approach. So one possible solution to this intractable problem is sampling based approach. And when I say one possible, naturally I mean that there are other possibilities also. You can do it again in an approximate sense, even without using sampling, but that we will talk later. Right now we will be talking about sampling. So let us put it this way, that one possible solution to this intractability is to use sampling based approaches. Clear? So the reason for sampling based approach is clear. Why we need sampling based approach? Obviously, what is sampling based approach? We will come to that later. But why we need sampling based approach? I hope that is the motivation part is actually at least clear, right? Okay. So one possible solution is to use sampling based approach. Okay. One possible solution is to use sampling based approach. Clear? So now, before we go to sampling based approach, or before we go into details of sampling based approach, how does it work? What do you think is the broad idea of sampling based approach? The broad high level idea of sampling based approach is that instead of working with distribution, you will work with samples. Samples drawn from distribution. So yes, you cannot compute the posterior, but can you compute at least some samples of posterior? And can we take those samples as representative of the posterior? So that is the big high level idea of sampling based approach, is that instead of working with distributions which are intractable, we now want to work with samples. Okay, that is the high level idea. So the high level idea in sampling based approach or approaches, it's not one approach actually, approaches is to work with samples drawn. The high level idea is to either work with samples drawn or work with samples in lieu of the distribution. Okay. So the idea is simple. Suppose I have a Gaussian, 2D Gaussian distribution, and for a 2D uncorrelated Gaussian, we know the contour will look something like this. So this is my distribution, right? The contour, if I draw, it will look like this for 2D. The idea is that this distribution I cannot work with. What I will do is I will work with samples. So this samples which are placed here with certain probabilities, and we will only work with these points instead of the distribution. So this idea already has been introduced through practical 0, how to draw samples and all those things. That was one of the idea of practical 0. Those who have done know that you have seen that how you can draw samples and all those things. So the idea is that we will work with those samples and not with the distribution. So all the operations will now be on the samples, and then you will compute statistics and all those things using the samples. Okay, so that is the high level idea. But now let us try to understand a little bit mathematically, hopefully, that why this should work, why sample should work, or is sample enough in it, or is it good idea to work with samples in place of distribution? And does this idea even work? Like, I am telling that you can work with samples, but why should you trust me? There is no reason for you to trust me until and unless I prove it to you, or I show you some theorem which someone else has proved that yes, this can work. And that theorem is known as the law of large number. So all these sampling based approaches are rooted in a theorem known as the law of large numbers. So as I said earlier, there are two formulas, right? The product rule and the sum rule. These are the most common formulas. Along with that, there are two theorems also, central limit theorem and the law of large number. So these four things are the core of this whole course. The sum law and the product law, and the law of large number and central limit theorem. Central limit theorem we have already introduced in the process of taking epsilon to be Gaussian. So now let us introduce the law of large number. Okay. Law of large numbers. Okay. And the idea of law of large numbers is that suppose we have xi, okay, suppose xi for all I are IID. Remind me, what is IID? What is the full form of IID? Independent and identically distributed. Okay. So suppose xi for all I, or I, and when I say for all I mean I varies from 1, 2, 3, 4 and can go as high as I want. Okay. Or IID. And we define xn bar is equal to 1 by n summation over I xi. Okay. So what have we done? We have defined xi for all I as IID, and xn bar we have defined as 1 by n summation of I xi. Then the law of large number states that for sufficiently large n, this xn bar will be equal to mu almost surely. Okay. So then, as per the law of large number, xn bar is equal to mu almost surely as n goes towards infinite. Okay. Almost surely, what does it mean? It's a mathematical term. We will not need it. For us, it will be mu approximately equal to 1 by n summation xi. What is mu now? What is mu? I have not defined mu here. So you should ask, right? What is mu? So I said xi are IIDs. So that means they are some distribution, identical and independently distributed. So there is some distribution there. So mu is the mean of those distribution. Okay. So this is basically telling you that if you want to compute the population mean, if you take enough large sample and take the mean, that is representative of the population mean. In a very simple words, that is what it is saying. That suppose you want to calculate the population mean, but you cannot calculate because the population is very large. If you take large enough samples randomly and take the mean of that sample mean is the population mean. That's what it means. Clear? And by the way, this is not just the law of large number, this is known as the strong law of large number. Okay? There is a weak law of large number as well. And weak law of large, in weak law of large number, we represent, instead of equal to, we write it in terms of probability. It will be probability of something less than epsilon, and in that sense we will write. I am writing only the strong because that's what we will use. Okay? But you should know that this is the strong law of large number because you are making a very strong statement. In a weak statement, it will be in a probabilistic sense. Okay? Whereas in a strong statement, it will be in a definitive sense. So this is more like in a definitive sense. So it's a strong law of large number. Okay, so this basically says that if n goes to infinite, this will be equal. That's all. Okay. So this basically tells you that you can work with samples. Instead of the population, you can work with samples. Given that your sample size is sufficiently large, you can work with samples. Clear? This is what it means. Now, if I generalize it, so generalizing, I can write expectation of gx, where gx some arbitrary function, this is equal to integration gx fxx dx. Okay. Clear? This basic definition of expectation, right? And then this will be equal to, approximately equal to 1 by n summation I equal to 1 to n g of xi, where your xi is drawn from fxx. This is what you did while computing the area of the, while computing the value of pi in practical 0. This is exactly what you did, right? So what is the idea? See, it is basically saying that if you want to compute an expectation, you don't need to solve this integration. And integration is our bottleneck, remember, the denominator. So basically any integration you don't need to solve. All you can do is you can draw samples from the distribution, which is fxx, and use those samples to approximate it as a summation. And summation we are very good with. We can solve summations, right? So that is the fundamental idea that it is talking about. Okay? That is the fundamental idea that it is talking about. Okay? Any questions till now? Otherwise, we will solve one problem, a small problem. So if there is no question, let us try to solve one problem and then we will come back to this. We will need this, or at least the last one, but let us solve one problem before that, okay? So suppose we consider the game of throwing a dart. Everyone knows about dart? So it's this kind of thing you throw. There is a circular part. If you hit the middle, you get 10 points. And if you go away from the center, you get 9, 8 and some points like that. Okay. So let us consider a game of throwing a dart. Okay. So let us consider the game of throwing a dart. Okay. And as I said, the dart means you have a circular kind of thing. Let's say that we have a circle which is inscribed inside a square. Okay. So basically, I have something like this, which is a square. And I have a circular portion like this. Okay. And to get any point, you have to hit the circular portion. If you hit outside the circular portion, you will get 0. So you will not score any point. So to get any point, the circular portion is where your dart should hit. Okay. So now, what is the probability? Is the probability of scoring. And let me give you some more data. So these corners are -1, -1, -1, -1, 1, 1, this is -1, 1. Okay. So this data is given to you. The problem statement is clear that you are throwing a dart. The dart should hit the circular portion for you to score anything. If you hit outside, you don't score anything. And we are assuming that when you are throwing, it will actually hit and stick. It will not that it will fall down. So that is an assumption, okay? Because that do happen. So now, this is a very simple problem. What is the answer? Theoretically? Theoretically, what will be the answer? I don't want the numbers, but how will you compute? Let's put it this way. Correct? Obviously, it will be the area of the circle by area of the square. So theoretically, we know that. So theoretically, what am I writing? Theoretically, we know that probability of D, and D is the dart, okay, D is the event of throwing a dart belonging to A is the circular area, is equal to, as correctly said, area of the circle divided by area of the square. Okay. Now, if I write it in integral form, because area can be computed as an integration, this is equal to integration over dx dy, and this integration is over the area A, or that is the circular area, divided by integration S dx dy, where S is the square area. Make sense? Simple. Now see what I am writing, whether that is making sense or not. Integration of S I A d dx dy divided by integration over S, not I, sorry, integration over S dx dy, where your Ix or Ia in this case, IAD has a name. It is known as the indicator function. Okay, so it indicates. And what does it indicate? And how does it indicate? It is equal to 1 if your dirt belongs to A. So by the number 1, it is indicating whether you have hit the area or not, or 0 elsewhere. So it indicates by yielding a value 1, okay, that you have successful, or 0 that you are a failure. Clear? So now tell me whether the last integral is making sense or not. What have I done? Think about it. What I have said is that I will not integrate over the circle, I will integrate over the square, but whatever area comes outside the square, I will make it 0. And whatever comes outside the circle, I will make it 0. And whatever area comes inside the circle, I will make it keep it as it is. That's what it is saying. If you really want, what you can do is you can write that S as two integrals, integral over A, IA dx dy, plus integral over S minus A dx dy, and in that case S minus A will go to 0 and you will get the same thing. So that means any integral, if you want, you can write using an indicator function. And this indicator function is an important concept used throughout statistics and many other domains. Okay. So this is the indicator function. So this is clear. Now what is the denominator? What is the numbers? What is the outcome of the denominator? What is the area of the square? 4, right? Minus 1, 1, 1, I think that is the I took. So then this is equal to, so therefore probability your D belongs to A is equal to 1 by 4 integration over the square I A D dx dy. Make sense? All I have done is that the denominator I know is 0, is 4, so I have just put it. Okay? Clear? And it is 4 because just calculate the area, you will get 4. Okay? So now, this should be very simple. I A D 1 by 4 dx dy. Okay? 1 by 4 I took inside. Now what is 1 by 4 apart from area or 1 by area? Can you think of anything else about 1 by 4? You should be, because this was the same thing we did in practical 0. So in that case also 1 by 4 was coming. And what was 1 by 4 in practical 0 for computing pi? What was it? It was a bivariate uniform distribution in -1 to 1. What is the PDF of uniform distribution? 1 by b minus a. So if it is varying from -1 to +1, what is the distribution? 1 by 2. And if there are two variables in 1 by 2, they are independent, then it is 1 by 2 multiplied by 1 by 2, which is equal to 1 by 4. So this that you see here, this one is nothing but a uniform distribution, multivariate, where one varies, the lower limit for both is -1, and the upper limit is 1, 1. Or you can think of it as u -1, 1 multiplied by u -1, 1, and I will call it as US, which is uniform distribution in the square. So S stands for square. Okay, and remember that A comma B is equal to 1 by b minus a, where a and b are the lower limit and upper limit. This is the PDF. Okay. Okay. So this 1 by 4 I can write as US, which is a bivariate uniform distribution. Okay. If that is the US, which is the uniform distribution, then what is that integral? Is it some statistical quantity? Or can you relate that integral with some statistical quantity? A quantity that I probably showed 2-3 slides ago. So can you relate this integral in black, second line, with some statistical quantity? What is it? Of? Correct. What did I show 2-3 slides ago? Expectation of gx is equal to integration of gx fx dx, where fx was the PDF. Now your PDF is uniform. So same form. So this is equal to expectation of the indicator function. So this is equal to expectation with respect to the uniform distribution of the indicator function. Right? So we have proved that the probability computation, because the probability is what we want to compute at the top left, the probability that we want to compute boils down to computing a expectation. Right? And now let us do one small thing. We'll again come back to this, but let us now give you another scenario. Okay. So it is the same example. Let me go back. So it is the same dart throwing example, but now I am also giving you some information that suppose you have thrown the dart n number of times. Okay. And out of those n, k times you have hit the circle. So then again, by common sense, what is the probability of getting a point with this setup now? K by n. If I have thrown n times and hit it k times, the probability is k by n, we know that. So that's the common sense answer. So now the question is, this is the analytical answer. This is nothing, this is the analytical answer, right? So now whether this analytical answer can give you the common sense answer is what we want to find out. Okay. So now, using common sense, we know that if we throw the dirt n times and hit the circular portion k times, then probability of D hitting the area is approximately equal to k by n. We know this is our common sense estimate, right? Correct? So let us call it equation 2 and let us call this equation 1. So the question is, can equation 1 and equation 1 and equation 2 are supposed to be same under the assumption that n is very large. So can we show it? So this can be proved by using law of large number on equation 1. So if I use law of large number on equation 1, what will I get? What I have got till now is this. Indicator function. This is what I have got. Now what this expectation, if I write it using law of large number, how will it look? This expectation, if I write it using law of large number, how will it look? Summation, 1 by n, summation I equal to 1 by n, 1 to n, then the indicator function evaluated at different throw of the dirt, di, where the different throw of the dirt is coming from the uniform distribution. So this is equal to 1 by n, summation I equal to 1 by n, IA di, right? And this is coming directly from, if I go back, this is coming directly from the law of large number here, right? So I have just used this expression, the second expression, and that gives me this. So now you tell me, what is that summation equal to? What will be that summation equal to? K. Why? Because suppose I throw one time, I will either hit it or not hit it. If I hit it, I will get a 1 score. If I don't hit it, I will get a 0 score. So now if I hit k times, I will get k score. So this summation will be equal to the number of times you have hit the target. So that should be equal to k by n. K and 1 by n is there. So this is equal to k by n. Actually a trivial proof, but it is important to understand this, because otherwise you will be using sampling method blindly. Okay. So that's why this proof is important. Okay. Any question on this part? Otherwise we will go back to this and see what more can we do with xi. So any question? No? Okay. So if there is no question, so let us now proceed. So we have already written in the generalized form that expectation of gx is equal to integration of gx, the same equation I am writing, nothing new, dx. This is approximately equal to 1 by n summation I equal to 1 to n g of xi, where xi is coming from fx x. Okay. And this sign, this one you see, this means that fx, this symbol means xi is a sample drawn from that distribution. That's what it means. Okay. So now how many of you know about direct delta function? How many of you know about direct delta? What is the direct delta function? Not a Kronecker delta, direct delta.
functions at the table by multiplying direct delta functions, then we will get the that.
True, but true, and that definition I will use. But in general, direct delta function, what is the value at that point? The function, you get the value of the function, you are right, but what is the value of direct delta function? So you can imagine the direct delta function as kind of a spike at a point, impulse, but that spike value is kind of infinite. But the area, if you calculate, it is equal to 1. So direct delta function is used, or is actually the PDF for deterministic function. So if there is something deterministic, what is the PDF? It is the direct delta function at that point. So PDF of deterministic function is represented using direct delta function. Okay, because at that point it will pick, and at all other points it will be 0, and the area will be equal to 1. That's the definition. Okay. So let us introduce the direct delta function, and the definition you provided is correct. Direct delta function, it has many utilities. So this is, I will write it as delta theta naught theta. Okay, this is how I will write it, which means it will peak at when theta is equal to theta naught. Everywhere else it will go to 0. Okay. So this also means, so direct delta, how do you define it? So if you have an integration f of theta and you multiply it with a function, and if that output of that gives you f of theta naught, so if this relation holds, then that delta function is known as the direct delta function. Okay. So then if this relation holds, then this is the direct delta function. Okay. So then this is the direct delta function. So now let us consider a scenario where I have a distribution, let's call it pi of x. So I have a distribution pi of x, and from that pi of x distribution I have drawn n samples. There will be xi, x1, x2 and something like that. So suppose we have n samples from pi of x. So pi of x is a distribution. Pi of x is generally used as a term, I will be using it throughout for the sampling part, as the target distribution. So right now you don't need to understand what target means, but general target means the distribution from which you want to sample. So in that sense you have pi of x, and you have, so that means you have xi drawn from pi of x, and I equal to 1 to n. Okay. That is from 1 to n. So you have n samples. So now do you think these n samples will represent the PDF exactly, or do you think there will be some approximation? What do you think? If n tends to infinite, that's the exact kind of representation, almost surely. But in this case, I'm not saying n equal to infinite. I'm saying n is some finite number. I'm not even saying small, big, nothing. So now the question that I'm trying to pose is that, using these n samples, how can you represent pi of x? So the question I'm trying to pose is, how to represent pi of x using xi. Okay. And this might not be directly needed, but this is something that can be useful and in proving certain things later. So how do you think you will represent it? Just now I said that direct delta function is what? It's like a PDF of a point, deterministic. Now, once you've drawn the samples, those samples are deterministic. What you will do is that you will put direct delta function on each of these points and then take an average of that. Okay? Because if you have n points, area of each direct delta function is 1. N points, the area will be equal to n. Divide by n, you will get 1. So that is known as the empirical PDF or empirical representation of the target PDF. So this is represented as pi of x is approximately equal to 1 by n summation over I delta, okay, x, right, not theta, delta xi of x. Okay. So it is like saying that at each of the points you have a direct delta function and then the average of that. What is the area equal to each of the direct delta function? If you integrate, it should give you 1. So the summation will give you n by n 1. So that's the valid PDF in that sense. Direct delta function cannot take negative. So again, that's a valid PDF. So this is known as the empirical representation of pi x. Yes. So I have some distribution pi x, right? From there, I have drawn n number of samples. Now those samples when I have drawn, can they change? They are fixed. So they are deterministic. How do you represent a what is the PDF of a deterministic sample? Delta. What is the PDF of n such deterministic points? Each of them will be delta but centered at different point. So this theta, delta of xi, that xi will change, right? Now those points combiningly are representing the distribution. So you can think of that, okay, the average of that is this distribution. So you will take a 1 by n, and if you want to prove that whether this is a valid PDF or not, take a summation integration. Integration of delta xi will give you 1. N delta xi will give you n. N by n will give you 1. And not only that, you go back. This fxx is there, right? Go and put that distribution there. So the top line, instead of fxx, if I put this one, what will I get? Integration of gx and then summation delta xxi, and then the summation and integration can interchange, and what will you end up getting? The exact same thing. So let us show you. So suppose I want to calculate E expectation of gx with respect to pi, okay? You know that this is equal to gx pi x dx, right? Now pi x, how are we approximating? Using the empirical distribution, let us put it there. So this is approximately equal to then integration gx 1 by n summation over I delta xi x dx. The summation and integral will interchange, 1 by n will come outside. This is equal to then 1 by n comes outside, summation integration of gx delta xi x dx. What is this integration equal to? From the definition of direct delta function, gxi, that is the definition. So then what do you get? 1 by n summation gxi. So clearly whatever law of large number is saying, you can prove it with this. So that also again establishes the fact that this is the correct empirical distribution. Otherwise you would have not gotten this. So therefore, expectation of pi is approximately equal to, you get the same result, of xi. Okay. So that is the empirical distribution. Similarly, if I want to if I have a bivariate distribution, how will it look? So bivariate case, I will have pi of theta 1 comma theta 2. This will be equal to 1 by n summation over I direct delta function theta 1 I theta 2 I theta. Same thing. If I have to find out the, I don't know, variance, I can again find out the variance. Variance is nothing but an expectation of the second of the square term. So variance is what? Variance of, let's say, gx. This is equal to expectation of gx minus mu whole square. I have my expectation. Now I use the law of large number that will represent it as a summation. So this then is equal to 1 by n summation I equal to 1 to n g of xi minus mu square. Okay, where mu you have already calculated in the top line. Clear? So basically, once you have the samples, you can use the samples to compute the empirical distribution, and from the empirical distribution you can find out closed form solutions of so many things. Okay. If you want to do the map, what will you do? How will you find out map? Map is maximum a posteriori estimate. So how will you find out map? Simple, you will draw samples and you will check which sample has appeared the most number of times. That is the frequency. So that sample has the highest frequency. So that should be the map estimate. So basically everything can be done with samples, given you can draw samples. And the question is how to draw samples. And that is what we will discuss starting this point till the end of sampling method. So the point is not about using sampling, that we have discussed and that is done. And we now know that if you give me samples, I can do many things. But who will give you those samples? No one. So the question is how to draw samples. Well, that's what we will study now. Okay. So given samples, we now know that all quantities of interest can be computed with certain level of accuracy, right? Right? But how to draw samples? Who will give you the samples? No one will give you the samples, so you have to draw samples. So how to draw samples? So, but how to draw samples? Okay, how can we draw samples? So now let us see how can we draw samples, and let us talk about the most basic method, which is known as the inverse CDF method. Okay, so let us see. So suppose we have our target distribution. So now I am using the term target because target distribution is the distribution from which you want to sample. Okay. So target distribution is your distribution of interest. We have our target distribution pi of theta, let's say. Okay. Okay. We have our target distribution, and so this is the distribution from which we want to sample. So if pi of theta is Gaussian, we want to sample from Gaussian. If pi of theta is uniform, we want to sample from uniform. Okay. The question is how to sample from pi of theta. Okay. So before we discuss how to sample from pi of theta, there is something that you need to know, and that is that there are standard algorithms that allows you to sample from uniform distribution in 0 to 1. So there are already standard algorithms that allows you to sample from uniform distribution in 0 to 1. Okay. And we will not talk about that algorithm, because that's a statistical course, that is part of some statistical course, right? Our goal is simple. Our goal is that given that algorithm, so given that algorithm that can give you sample from uniform distribution in 0 to 1, how can we sample from some pi theta? Okay. So there are standard algorithms that can sample from uniform in 0 to 1. Okay. There are some standard distributions that allow you to sample from 0 to 1. Okay. So our problem then boils down to using u I, which is coming from you, how can we sample theta I coming from pi theta? Is the problem statement clear? Because we are not actually sampling, we are kind of saying that we know how to sample from uniform, now how to transform it. Or in other words, we want to sample from pi of theta given we know how to sample from uniform. So is the problem statement clear? The solution will come later, but is the problem statement clear? Clear what we are trying to do? So if you remember, in practical 0, there were questions where you were asked to sample from Gaussian. So the idea is now you can sample from uniform. Using those, can you sample from Gaussian? So that is the kind of statement we are looking at. Okay. So let me first give you the algorithm, and then I will prove why that algorithm works. Okay. Algorithm. It is a 2-line algorithm, probably the simplest algorithm you can ever have. Okay. So the first sample is first you will sample ui from uniform, and then you will have xi is equal to fx inverse ui, and you will return xi. The simplest possible algorithm there is two-line algorithm. First line you sample from uniform, second line you transform it. What is fx inverse? Fx inverse, first let me define fx of x is known as the CDF, cumulative density distribution function, which is equal to integration minus infinite to x pi x dx. Okay. This is your CDF, cumulative distribution function. So this is your CDF, and fx inverse is known as the inverse CDF. And the method is known as the inverse CDF approach. This method, this algorithm is known as the inverse CDF approach. Okay. Is the algorithm clear? Why it works, I am coming to that. That will probably be the last or the second last thing for today. But is the algorithm clear? Okay. Any question on the algorithm? If not, then if there is no question on the inverse CDF approach or the algorithm, but how do we know it works? It works, or rather how to prove that it works. Basically, how can you prove that this xi that you are getting is from pi x? Because if you can prove that xi is from pi x, then that proves that this method works, right? Because your objective was to sample from pi x. So, in other words, how do we know that xi obtained from the inverse CDF approach is from pi x? This is what we have to prove, right? And this xi should be for any I, right? This is what we have to prove. So let us see. Our transformation, what is the transformation? X is equal to fx inverse u. This is the transformation we have used, correct? So then probability of, or rather let us see, then f, or probability of x less than equal to x, let us say, is equal to, how do you write it down? What is probability x less than equal to x? What is this quantity first of all? CDF. And how do you write it down? Integration minus infinite to x fx dx. So this is equal to integration minus infinite to x, fx is my pi x dx, right? Correct? Now, how are you getting x? What is the transformation we are using on x? F inverse u. So let us put it there and let us see if we are getting something meaningful. So 3, 4. Substituting 3 in 4, we get probability x less than equal to x. So I will write fx inverse u. U less than equal to small x this is equal to probability of u less than equal to fx x. The inversion I can take to the right hand side, because CDF is the monotonically increasing function, so that's why I can do that. Okay. So then this is equal to integration minus infinite to fxx. Tell me, have I written it correctly or there is some mistake? In the integration term till now. Should it be from minus infinity? What range? What should be the lower limit? 0, because now it is an uniform, and uniform is from 0 to 1. So I can write minus infinity, that will be of no meaning. So I will not delete it, I will write it like this so that you know. Okay. And then what is the PDF of u? What is the PDF of u? One by b minus a, b is 1, a is 0, so 1 dx, which is equal to, what will you get? fxx, right? And what is fxx from definition? This is equal to, from definition, right? So what have I proved? I have proved that from the transformation, whatever CDF you are getting, the samples, the CDF that the samples is following is exactly same as the CDF of pi x. So instead of proving through PDF, I proved through CDF. So this naturally proves that with that transformation, inverse CDF transformation, whatever samples you will generate, that is from as if you are generating samples from this pi x, because only because of that CDF is equal to this one. Clear? Let me repeat once more. I wanted to prove that with that transformation fx inverse u, whatever samples I generate is from pi x, because only then I can claim that okay, I am generating from pi x. So this is equivalent to providing whatever samples I generate from that transformation follows the same CDF that you will get with pi x, right? And that is exactly what we are getting, which means this proves that this transformation does generate samples from the target distribution. Okay. So this proves. Okay. However, remember, for this course, this is of no use. Okay. This is the most basic one, but is of no use, because this you can only use, when can you use it? When first of all pi x is known. In your case, pi x is not known because the denominator is not known, right? This can only be used when you can find out the inverse of CDF. In your case, if the PDF is not known, forget about CDF being known. So this is of no use for this course, but this is the most basic one. So we got everything that you cannot do in this course out of the picture. From next lecture, we will do things that are applicable for this course. Okay. This was to motivate and the need for sampling and the basic sampling. But things that you can actually use in practice for Bayesian machine learning, we will start from next lecture. Okay. Thank you.